Welcome everyone to this section on creating databases and tables. So far, we've really only focused on querying and reading data from an existing database and an existing table. We are now going to shift our focus to creating our own databases and tables using SQL commands. So for this section, we're first going to discuss a few theoretical concepts such as choosing a data type, primary and foreign key, as well as constraints. Then we're going to move into actual SQL commands to perform the creation of a database or a table using create, insert, update, delete, alter, and drop. So as I mentioned, we're first going to focus learning a few theoretical concepts, such as choosing the correct data type for a stored value and setting possible constraints on it, which means the first few lectures in this section are just going to be slide lectures. Then we'll also learn about things like primary and foreign keys. Once we learn these theoretical concepts, we'll move on to actually learning the SQL commands to implement them. Okay, with that being said, let's get started. I'll see you at the next lecture. Welcome back everyone to this lecture on data types. We've already encountered a variety of data types that we've seen when calling off columns from an existing table. Let's quickly review the main data types in SQL, since when creating a table, we'll have to choose what data type each column should hold. So here are some data types, the main ones that we've already encountered. There's the Boolean data type, which is just true or false. There's character data types, such as car or care, variable car, and text. There's numeric data types, like integer and floating point number. And then there's temporal data types, things like date, time, timestamp, and interval, as well as timestamp with time zone. So we have these generalized categories that we're familiar with, and then we actually have data types within those categories. Some other not as common ones are things like UUID, or Universally Unique Identifiers, which is essentially an algorithmically unique code in order to make sure you have a unique identifier for a particular row. Then you also have things like arrays, which store an array of strings, numbers, etc. You can also store things like JSON. There's HStore, which is a key value pair, and there's special types such as a network address and geometric data. Now, when creating databases and tables, you should carefully consider which data type should be used for the data to be stored. And typically what you should be doing is reviewing the documentation to see the limitations of the data types. And you can check this out at postgresql.org/docs/current/datatype.html. And it reviews all the subsets of the data types that we just mentioned. So we have the general categories, and then we have the particular data types. So to show you an example of what this would look like, let's imagine we want to store a phone number. And we start thinking, should it be stored as a numeric data type, such as a large integer? And if so, maybe what type of numeric? Should we be storing it as just a normal integer, a big integer, etc.? So we decide we have this task of storing a phone number. And we decide, should we store it as numeric? Well, first thing we should do is take a look at the online documentation for options. And if you go to that documentation page, you'll see a table that looks something like this, where you have the name of a specific data type under the general numerical data type categories. And we can see here we have a bunch of different options. We have small integers, which has a storage size of 2 bytes. We have integer, storage size of 4 bytes. Big int or big integer for 8 bytes. We have a general description for these, like small range, typical choice, and then large range. And you'll notice that as you get larger in these possible ranges, then the storage size becomes larger. And for a phone number, notice that if we just chose small int or small range integer, that actually doesn't have enough integers or digits for us to store a typical phone number. And then notice we also have other things like decimal, double precision, etc. These are things that are unlikely to be needed for a phone number. So you might be thinking, well, based on the fact that phone numbers can have extensions or maybe leading zeros, I'll choose something like big int or a large range integer, since it looks like these numbers are large enough for me to store a full phone number. Well, as I mentioned, based on those limitations, you may think it makes sense to store it as big int or big integer data type. But we should really be thinking about what is best for the situation. Remember, we're storing phone numbers, so why bother with numerics at all? We don't perform arithmetic with phone numbers. So it probably makes more sense to just use some sort of text data type, like a variable character data type, because you're not going to be adding phone numbers together or subtracting numbers from a phone number. Once you have a phone number, it's pretty much set. So it probably makes more sense to just store it as a text data type instead of having to even think about the possible range that is allowed for you if you go with a numeric data type. In fact, what I would recommend you do is always search for best practices online. And you'll quickly discover, if you were to just Google search how to store phone number PostgreSQL, that it's usually recommended to store as a text-based data type due to a variety of issues. Things like, and like I mentioned, there's no arithmetic performed on a phone number typically. You're not adding two phone numbers together to get a new phone number. And also, things to be careful of is, especially when it comes to country codes, that leading zeros could cause issues. When it comes to numerics, 7 and 07 can often be treated the same. However, they're definitely not the same when it comes to a phone number. So if you Google search just best practice phone number PostgreSQL, you would discover that pretty much everybody recommends to store it as a text-based data type, or, depending on additional libraries being used, as an actual phone data type. Now, keep in mind there's no built-in phone number data type for PostgreSQL, but you can install additional libraries specifically designed for that. But for our use case, it probably makes the most sense to just store it as a text data type. And these are the sort of considerations you should be thinking of when building out your own tables and your own databases. Often, just the internet's your friend. Pretty much everyone's already solved these sort of problems already, and there's usually something you can easily Google search for best practices. So, when creating a database and table, also take your time to plan for long-term storage. Remember, you can always remove historical information you've decided you aren't using, but you can't go back in time to add in information. This goes along with what we discussed during the timestamp and extract lectures. You can always just remove historical timestamp information, but you can't go back in time and add in more information. So it's usually easier just to record more information than it is to have to limit yourself for long term. All right, with that being said, the main things to consider here is always do a quick Google search for best practices, and definitely refer to the documentation to see your full range of options for data types when it comes to storing your data. Thanks, and I'll see you at the next lecture. Welcome back, everyone. In this lecture, we're going to be discussing primary and foreign keys, fundamental concepts necessary to understand in order to create tables in SQL. Let's start with a primary key. A primary key is a column or a group of columns used to identify a row uniquely in a table. For example, in our DVD rental database, we saw customers had a unique non-null customer ID column as their primary key. Unique means it has to be distinct for every row, and non-null means there must be an entry there for the primary key. Primary keys are also important since they allow us to easily discern what columns should be used for joining tables together. So let's see an example of a primary key. Here's a subset of a screenshot where we selected everything from a customer. Notice that we have this customer ID column, and PgAdmin, when you grab table information, it will actually tell you if a column is a primary key for that table by specifying PK, or primary key. And so notice this is a unique integer, and it's also non-null, which essentially means that every row must have an entry here for customer ID. So this is a customer ID integer that uniquely identifies each customer. You wouldn't want to use something like the first name as a primary key because people can share the same first name. However, they cannot share this unique integer ID. So again, it's integer-based and unique. Later on, we're going to be learning about the serial data type, which is actually a way of automatically creating these unique integers for us as we enter more data into a table. Now let's discuss a foreign key. A foreign key is a field or group of fields in a table that uniquely identifies a row in another table. A foreign key is defined in a table that references to the primary key of the other table. The table that contains the foreign key is called referencing table or child table. The table to which the foreign key references is called reference table or parent table. A table can have multiple foreign keys depending on its relationships with other tables. So for example, recall in the DVD rental database payment table, each payment row had its unique payment ID, which was a primary key for the payment table, and it also identified the customer that made the payment through the customer ID. The customer ID within the payment table is a foreign key, since it references the customer table's primary key. So for example, let's check out and grab a subset here from the payment table. So technically we're grabbing all the columns, but the screenshot only shows a subset. Notice that for the payment table, we have this payment ID, and PgAdmin lets you know that it's a primary key because it has PK there. So we have this payment ID, which is a unique identifier for every single payment row. However, you'll also notice that we have other IDs. These other IDs are foreign key references. Now, PgAdmin won't directly tell you through a simple query call whether or not a column is a foreign key. We'll discuss how to figure that out in just a little bit. But here we can see we have these customer IDs, staff IDs, and rental IDs. Notice that within the payment table, it's okay if they're repeated because the same customer may have made multiple payments. So these foreign keys, the reason they're foreign keys is they're a reference to a primary key in another table. So customer ID is a foreign key within payment because it's a primary key within the customer table. Same with staff ID, it's foreign within payment because it's a primary within the staff table. Same with rental. And again, PgAdmin won't alert you directly in a simple query call whether or not this is a foreign key. They'll only do that for the primary key. Now, you may have already realized that a primary key and a foreign key typically make good column choices for joining together two or more tables. When creating tables and defining columns, we can use constraints to define columns as being a primary key, or attaching a foreign key relationship to another table. And we'll discuss this in more detail when we actually go over the create commands. However, I mentioned that in a simple query call, PgAdmin only directly alerts you to something being a primary key and not a foreign key. I want to quickly explore the table properties that are available to us in PgAdmin in order to get information on primary and foreign keys through the properties window, since we can't really see them directly through just a simple query call. Let's jump to PgAdmin and show you how to understand the foreign keys that are present within a table. Okay, here I am in PgAdmin. Recall that we had this example query select everything from payment, and I can see here that every single payment has a unique payment ID as a primary key. But also notice that we had customer ID, staff ID, and rental ID. And just from this query, we can't be 100% sure that it's a direct foreign key. Now, given how much we've worked with this DVD rental database, we do understand, and we're pretty familiar with the tables enough to understand that this customer ID, staff ID, and rental ID are foreign keys. But how do we actually understand that officially? How can we see the dependencies? Well, if you take a look at DVD rental, we can go ahead and expand schemas here. Give that a little time to load. And as that's expanding, what we're going to see is the public relationships, and then we have tables. So expand on tables, and then we have, scroll down, let's go ahead and look at the table we're looking at right now, which is the payment table. And then we can expand on this, and we can view the columns here. So we have payment ID, customer ID, staff ID, etc. Now, if something is a foreign key, that is technically a constraint on that particular column. And we're going to be discussing constraints in more detail in the next lecture. So let's expand constraints. And notice here we have certain keys. So there's actually a little key symbol. The golden key symbol is the primary key. So this is the payment primary key. So payment underscore P key for primary key. And notice it shows you that customer ID, rental ID, and staff ID are F keys or foreign keys, shown with another little kind of dual key symbol. So the constraints here will actually alert you to the fact that they are foreign keys within this table. Now there are a few more ways to actually review this information officially. If you want, you can actually select one of these foreign keys. So notice that it's highlighted. And once you select that foreign key, over here on your tabs, right now we're just on the actual query editor tab, go over to dependencies, click on that, and it will show you the dependencies for that particular column and alert you to what tables it's referencing. So notice here we have this customer ID, which is a foreign key within this payment table, and it's referencing, notice here, the customer.customer ID, essentially telling you that under public schema, we have the customer table, and the customer ID is that primary key we're referencing. So you can view that under dependencies. One other way to do this is if you right-click on this, so right-click on that constraint and select properties, it'll actually show you the properties, and then you can expand on this to view columns, and it will tell you that it's referencing customer ID. So it's referencing that from the public.customer table. So that's just yet another way to actually view what actual primary key it's referencing as a foreign key within the payment table. So lots of different ways you can review this information if you're dealing with a database and set of tables that you're not 100% familiar with. So again, let's imagine we just ran our query, we see these ID columns, and we're not 100% sure whether or not they're foreign keys. We simply, underneath this little browser icon, we go ahead, view that table, view the constraints. Right away, this will tell you if they're foreign keys. If you want more details as far as what this actual foreign key is referencing, you right-click, go to Properties, go to Columns. It'll tell you the schema.table that it's referencing, and then the column it's referencing within that table. Okay, so that's how you can figure out more information based off what's available to you in PgAdmin for foreign keys. Primary keys, it's a little easier because any query should let you know if it's stated as a primary key constraint. Thanks, and I'll see you at the next lecture. Welcome back, everyone, to this lecture on constraints. Constraints is the last thing we're going to learn about theory-wise before we actually head into using SQL syntax to create tables. Constraints are the rules enforced on data columns on a table. They can also be used to constrain everything in a table, and we'll talk about that in just a second. So constraints are used to prevent invalid data from being entered into the database. This ensures the accuracy and reliability of the data in the database. Constraints can generally be divided into two main categories. There are constraints on a column, which constrains the data in a single column to adhere to certain conditions. And then there are table constraints, which are applied to the entire table rather to just an individual column. So let's talk about some of the most common constraints used. The first one is not null. So the not null constraint is pretty self-explanatory. It's essentially telling you that a column cannot have a null value. Essentially, if you're going to enter data into this row that includes this column, it has to actually include a value for this column. So for example, if you're creating a table that happens to take in customer information and you always need an email from them, then you can say that the email column has a not null constraint, essentially saying that you are required to provide an email for this customer, otherwise it's an invalid row and it won't let you add it to the table. Then another constraint that's really common is the unique constraint. This ensures that all values in a column are different. So a unique constraint could be used as something like a customer ID column because you want each customer ID to be unique. You wouldn't want to use a unique constraint on something like a first name column because people can definitely have the same first name. So unique, again, ensures all values in a column are distinct or different. Then there are primary key and foreign key constraints. We already learned about primary key and foreign key, but the way you actually define them when you're constructing your own table is you set them up as a constraint. So the primary key uniquely identifies each row or record in a database table, and a foreign key constrains data based on columns in other tables. So when you're setting up a foreign key, you'll actually also set up a relationship to another table you created. And there's two more column constraints I want to mention here. And check and exclusion are these constraints. They're a little more complicated, so I'm just going to give you the official definition for now, and they're going to make more sense in the next series of lectures when we actually programmatically use them. So keep that in mind. Don't worry about fully understanding these constraints because it depends a lot on the additional conditions you apply with them. So the check constraint ensures that all values in a column satisfy just some certain general condition. So you actually check against some sort of condition, such as has to be less than 20 or something like that. The exclusion constraint ensures that if any two rows are compared on the specified column or expression using the specified operator that you include with the inclusion constraint, that not all of these comparisons will return true. So don't worry too much right now about understanding check and exclusion because they actually depend a lot more on the additional conditional constraints you provide. Okay, so those are all available column constraints that you apply on an individual column. And you can also apply constraints across an entire table. And some of these table constraints just also use the same keyword that are used on the column constraints. So on a table, you can also have an additional check, and in parentheses, you pass in some sort of condition. So you check a condition when inserting or updating data across the entire table. You can also provide a references constraint, which is to constrain the values stored in the column that must exist in a column in another table. So it has to reference another column in another table. There's a unique column list constraint. So you pass in a list of columns into unique, so it applies across multiple columns across the table, and it forces the values stored in these columns listed inside the parentheses to be unique. So instead of just having something be unique within a column, it's going to have to be unique within multiple columns. So that's why this is known as a table constraint, because it's expanding it beyond just a single column. You can also do primary key on multiple columns, so it allows you to define the primary key that consists of multiple columns. Typically, when you're starting off, there's usually just one primary key column per table, but you can have multiple primary key columns per table. And if you wanted to set that up, you could do it using a table constraint, which is passing in multiple columns into this column list along with primary key. And that's pretty much it. So we understand a couple of core concepts in theory. We understand data types, how to choose data types. We understand primary keys and foreign keys. And then finally, we understand the options for constraints. These constraint options are going to make a lot more sense when we actually program them out in the very next lecture. So don't worry too much about fully understanding them right now. Basically, I just wanted to introduce the keywords to you. That way they didn't seem to come out of nowhere in the next lecture. So with all this under our belt for theory, we're ready to begin using SQL syntax to create tables. So let's go ahead and do that, and I'll see you at the next lecture. Welcome everyone to this lecture on the create keyword. Let's now learn the syntax to create a table in SQL using this create keyword and the generalized column syntax. So when you're creating a table, this is the full general syntax layout, and we're going to focus on just a couple of things here, and then we'll walk through some examples in PgAdmin. But let's go over the general syntax components. First, there's the create table, and then you choose whatever table name you want. So you would say something like create table payments or create table customers. Next are the columns that are within that table, and you'll choose the column name, then the data type for that particular column, and then you'll add in any column constraints. And you just have this almost as a list of different columns. Something to pay attention to are the fact that we use commas to separate out these columns. A really common mistake for beginners is they forget this comma at the end, and then you'll get some sort of weird error that's hard to actually diagnose. So again, just remember there's a comma there when we're dealing with the actual columns. Next, you add in any table level constraints that you want, so you can list off different table constraints, and we talked about those options in the constraints lecture. And then, in case you have some sort of relationship to another table, and you can inherit from an existing table. Now we'll talk about things like table constraints and the inherits command later on. For now, I really just want to focus on creating the table and setting up your columns. So we're going to follow along right now for this lecture with what I'm going to call common simple syntax, which is just creating the table and then adding in your columns. Let's work through a very quick example, and then we'll go over to PgAdmin and actually code it out. So for an example syntax, you would keep create table, those keywords don't change, and then you decide on a table name. So let's go ahead and make up a players table. Then we have to decide what columns are going to be in our players table. Typically what you're going to do first is you're going to choose a column to be a primary key. Typically each table should have a primary key. Obviously this may change depending on your circumstances, but let's go ahead and go with that. So we're going to have a player ID as the column name. We have to choose a type. And almost always, especially with PostgreSQL, when you're trying to think of a primary key, the type should be serial. So I actually want to focus in on this serial data type because it has some special properties. So in PostgreSQL, a sequence is a special kind of database object that generates a sequence of integers. And a sequence is often used as the primary key column in a table. So what serial is going to do, it's going to create a sequence object and set the next value generated by the sequence as the default value for the column. And this is perfect for a primary key because it logs unique integer entries for you automatically upon insertion. So that means as you're inserting more data into this table, you won't actually need to worry about providing a unique player ID yourself. Instead, Serial is going to do this for you, which makes sense because as you insert data, you're probably not going to know what actual player ID you're on as far as the integer count goes. So Serial takes care of this. So what's also nice about Serial is that if a row is later removed, the column with the serial data type will not adjust. It's not going to reformat everything in the serial. Instead, since it's not going to adjust, it's actually going to mark the fact that a row was removed from the sequence. For example, in this primary key column, as you're inserting players, you may see something like 1, 2, 3, and let's imagine we inserted 4, 5, 6, 7. And then later on, you decide to delete row number 4 because that player maybe left your team. What's nice about this is Serial is actually going to show that gap as the primary key. It'll show 1, 2, 3, 5, 6, 7, which means as you, as a user, go back to that table and see that you're missing number 4 from the primary ID column or primary key column, you know now historically that row 4 was removed at some point. So Serial takes care of a lot of problems for us automatically. It makes sure that each of these is unique because it's a sequence that keeps adding 1 based off the previous value, and then we ourselves, as we insert data into this table, don't need to even worry about providing a value for the primary key column. Okay, so you may already be familiar with this table. We mentioned it in the data types, and you'll notice that there's actually options for different types of serial. There's small serial, which is just 2 bytes, and it goes from 1 to about 33,000, so 3,000 to 767. And then we have serial, which is 4 bytes. It goes to a larger value. And then big serial goes to an extremely large value. So you can choose which one of these is appropriate for you, depending on how large your table is going to be. So we'll just go ahead and choose serial. Again, you could have chose small serial or big serial, but we'll just choose serial as our data type because this is going to be our primary key. Because this is our primary key, we actually type that in as a column constraint. So we set the table to verify this is a primary key. And then finally, let's go ahead and add in one last column. So let's go ahead and put the age of the player. So we have to choose a type for this. Again, you can go back to that table in the documentation, decide what types are appropriate. So if we take a look at this, maybe we decide that a small integer is appropriate. We don't need such a huge integer value range for ages, especially for people, because people can only go from 0 to a little above 100. We don't need the integer to go to some huge large number. So we'll go ahead and say that the data type is a small integer, and then the column constraint can really be whatever you want, but let's imagine that for some reason our league that these players are playing in is constrained by the age. Let's say players that are over 18 can no longer play in this league. So because of this requirement, we actually need to make sure that we know the age of the player, in which case we'll want to make sure that a column constraint could be something like not null, meaning that if you're inserting a player into this table, you cannot leave the age blank. Otherwise, the table will reject the new entry. Okay, so this is an example syntax of creating just a very, very simple table. So let's go ahead and actually explore some examples in PgAdmin and typing this out. All right, here I am inside of PgAdmin. To begin, I want to make sure we create these tables in a brand new database. That way we don't accidentally contaminate our DVD rental database. So what I want to do is, if you already have a query editor open, which you may have as you're following along with this course, you'll notice that it's open as a tab here. Note it says DVD rental, Postgres, etc. Go ahead and right click on this and just click remove panel. And it's going to ask you if you want to save any changes. We don't need to worry about that, so don't save. And that way we make sure that we don't accidentally run this query editor in DVD rental. The next thing we're going to do is we're actually going to create a new database. So underneath PostgreSQL, underneath databases, right click, go to create database. And then we're going to go ahead and you can really call this database whatever you want. I'll call it learning. And again, it's really up to you, but just for learning how to create databases and tables kind of makes sense. So you don't need to worry about changing anything else. Go ahead and click save. You should see learning appear here. Go ahead and click on it. And then just to make sure everything's working, after you click on it and you've made a connection, just hit refresh, and then we should be good to go. So after this, I'm going to right click on learning, and then I'm going to open up my query tool. And the query tool can not only be used for getting information from a database, but we can also run SQL commands to create tables from here. So that's what I'm going to do. And just to confirm that we're on learning with this query editor, go ahead and take a look at your tab here, and you should see learning here underneath the tab. Okay, so now that that's done, let's go ahead and create our table. So the first table we're going to create is just an example account table. So we have our first keywords, create table, and let's just say the table name is account. And then we have open and close parentheses. And here, over multiple lines, is where we can add in the actual column names. So I'm going to have a user ID column, and I'm going to set this as serial. And because it's going to be serial, the constraint I'm going to set on it is primary key. So this is going to be a primary key identifier that is automatically set up for us so that as we learn how to insert information into this table, we don't actually need to worry about inserting a user ID. Serial will take care of it for us. And that will make more sense when we talk about the insert command. So that's one column. Don't forget to put in your comma. And then we'll have a username. And technically you don't really need to worry about indentation or spacing, but just to make these line up so it looks a little nicer, we'll go ahead and do that. And then we're going to have just this be a variable character. And when you're using variable character, you have to pass in the limits of how long you allow this to be. So this could be a limit of, for instance, no more than 50 characters inside of the username string. And we want to make sure that each username that is set up here is actually unique. That way we don't accidentally have people with the same username. So we can set it up to be unique. The other thing we should probably set up here is that if you're setting up an account with us, we can't just have your username be blank. So we also want to make sure that it's a not null constraint here. So we have that. The next thing I'm going to set up here is a password column. So we can store their password. We'll have this be variable character 50 as well. And passwords, let's say we don't need to worry about them being unique. People can maybe have the same password, especially if this is not really a security threat. But we should make sure that they actually have a password. So we'll again say it cannot be null. And obviously there are things like security concerns that we're not really taking into account here when it comes to passwords. So very, very simple database, really just learning the syntax here. Let's go ahead and provide an email column. We'll have this be variable character as well. Let's say emails are typically longer than, let's say, a 50 character limit. Some people can have really long emails. So we'll go ahead and choose something like 250 characters available. And again, we want to make sure that there aren't shared emails. So the emails, just like a username, should be unique. And it should also be not null. The constraints is really going to depend on your specific situation. So keep that in mind. Every single table and database has its own unique situation, so I can't give you some general rules for what constraints you should provide on your own columns because that really depends on your business situation. And finally, let's go ahead and create some timestamp columns. Maybe we want to keep track of when an actual table is, or a row is created, like an account is created. So we'll say created on, and we'll have this be a timestamp. We'll have that be not null. And let's go ahead and keep track of when the person last logged in. So we'll say last login, and also have that be a timestamp. So if we scroll down a little bit here, just to see the parentheses that closes this all off, notice my very last column didn't actually need a parentheses because I'm not adding anything after that. And also notice that I'm not going to go ahead and say any constraints on last login because what I want to make sure that is even if you have just created your account, you won't really have a last login, which means if I said not null here, that may have created some sort of error. So created on should definitely be not null, but last login, I don't want some sort of error occurring if the person created their account but doesn't have a last login because they just created their account. So that's why there's no constraint here on last login beyond just the data type having to be a timestamp. Okay, so here's our create table account. Let's go ahead and run this. So when you run this, it'll say something like create table, query returned successfully. The data output shouldn't show anything because we're actually not asking for anything here. And if you see explain, pretty much all this should be blank. Keep in mind though, you can only run this one time. So take a look here underneath learning, schemas. we have the public schema, and then we have now tables. Expand on that, and you can see this new account table. So this account, if we expand on columns, I can see the columns I created, and I can actually also see some of the constraints I created. So notice here now we have a little primary key constraint, and on the account email key, it has 1 here, basically indicating that there was a specific constraint there. Okay, so we have that all set up ready to go. Something I want to again note, which is a really common error, is I'm going to induce an error by clicking execute again. If you click execute again, the error is actually relatively straightforward. It says relation account already exists, which makes a lot of sense. You don't want to accidentally create the table account again and then overwrite an entire table. So instead, PostgreSQL is going to just tell you, hey, you can't create that table, it already exists. Later on, when we learn about things like the alter command, we will be able to alter and edit existing tables. So we have this account table. Now what I want to show you is the ability to create another table and then link them through a foreign key. To show you this, we're going to start by creating 2 more tables. So we have this person with the account. Let's go ahead and create a job table. So let's say certain people can be assigned jobs later on. So we're going to say create table, job, and this job table will have a job ID column. And this is going to be a serial column, primary key, because it's a unique identifier for the job. And then the job will have some sort of job name or job description. So we'll say job name is the other column. We'll make this variable character. Let's give it a limit of 200. And then these should be unique. That way we don't accidentally have 2 jobs with the same name. And we can't have an empty job. So we can't just have a job ID with no job name. So here's our create table. Very simple for the jobs. Let's go ahead and run this. We should get back create table, query returned successfully. Remember, you can only run this 1 time. And now what I want to do is I want to create a table that references both the account and the job. Basically, it's going to be an intermediary table that connects someone's account to their specific job and when they were hired for that job. So this is going to be the table that shows us how to actually reference a foreign key. We're going to say create table. This is going to be the account job table, and it's going to have a user ID column. And this user ID column should be the same as the user ID in the account, which means it's going to be an integer type. Notice that I'm not saying serial. Serial should only be used as a primary key for the table that it's in. When you're using it to reference in another table, it's just going to show up as a normal integer, because serial is really just a sequence of integers. So because this is going to be a foreign key reference, I'm just going to say that my user ID is an integer, and then here comes the keyword, that references. And I need to tell it what column and what table to reference. So I pass in the table name, and then in parentheses, I pass in the column name inside that table. So recall, inside of this account, I have a user ID column. So the user ID column inside the account table will be the reference or foreign key reference for the user ID integer inside of the account job table. Now we're going to say comma, and let's do the same thing for job ID. So we will say job ID is also going to be an integer that references from the job table the job ID column. And then finally, let's go ahead and add in some column that basically tells the person when they were hired for this job. So let's say there was a hire date, and I'm just going to have that be a timestamp. If you want, you can optionally add in things like it has to be not null, but just to keep things simple, I have this hire date. Let's go ahead and run this. So I'm going to expand this a little bit, run this, and we should see query or return successfully. So now I have 3 tables. We come back here. Notice that right now it says tables 1. That's because I need to refresh this. So typically you're going to need to refresh every time you create a new table. Go ahead and refresh. That lets the database essentially know, okay, here are now the information on the 3 tables. I have job, account, and account. Account was that first table we created, and if I take a look at account job, taking a look at the columns, I have user ID, job ID, hire date. Then we have these constraints. And notice now we see essentially information that we have these foreign keys. You can check out our lectures on primary keys and foreign keys to refer to how you can confirm those sort of connections. Okay, so that's the very basics of creating a table with columns that have both primary key and foreign key references. Coming up next, we're going to learn how to insert information into the table. I'll see you there. Welcome everyone to this lecture on the insert command. As you may have already guessed, insert allows you to add in or insert rows into a table. The general syntax looks like this. We say insert into, decide on the table name, and then also clarify which column values we're going to be providing. And then we say values and add in a list of values. Keep in mind, you can also have a syntax for inserting values from another table. This looks kind of similar. We'll say insert into table, decide on the columns we're inserting to, and then we say select those matching columns from some other table where some condition happens to be true. So something to keep in mind, especially for the previous statement of inserting from another table, the inserted row values must match up for the table, including constraints. So if one of your constraints was that the column is not null, then you must provide a value as you insert, otherwise you'll get an error. If you're grabbing information from another table and inserting it into your table that you're currently using, then you must make sure that those actual columns also match up for things like data type. Another thing to keep in mind is that the serial columns, especially for those primary keys, they actually do not need to be provided a value. Recall that serial is a sequence, so it's going to automatically update the next available integer for that row. Okay, let's go ahead and actually work through some syntax examples using PgAdmin. All right, here I am inside of PgAdmin. Let's go ahead and recall what we actually used for our account table that we created previously. To do that, I'm going to, in my query editor, say select everything from account. Run this, and you shouldn't get back any data because we haven't inserted anything yet. And I can see here I have user ID, username, password, email, created on, and last login. Recall that user ID is serial data type, so I don't need to worry about providing that. And also recall that the last login column didn't have any constraints, so I don't need to actually provide one of those. Everything else, I believe, had some sort of not null or unique constraint, so we will need to provide. So let's go ahead and show you how you can insert into this table. We're going to say insert into, and then the account table name, which was just account, and then the columns we're going to provide. We're going to provide a username, a password, an email, and then we'll also say created on. And then after this, we're going to say values, and then we provide the list of values. So let's go ahead and choose a username. We'll go ahead and have the username be Jose. The password, typically you don't save passwords as strings in a database. There'll be a hashed version of a password, but just for learning syntax, we'll say that Jose's password was password. The email, we'll go ahead and have this be jose@mail.com, just a made up address. And then make sure we say created on, so check for that typo there. So created on, make sure that matches up. And now we're just going to provide a timestamp. And in order to save time, instead of providing a long string code for a timestamp that includes the date and the time, I can actually use from our timestamp lectures the current timestamp functionality. So I can say current underscore timestamp. And you can review the documentation and our timestamp lectures for a full list of these sort of timestamp function calls. So this is just going to insert those values here into the table. So let's go ahead and run this. And you should see something that says query returned successfully, etc. And under data output, we'll still see the same blank because we haven't actually asked again for the information from account. So let's go ahead and delete this. And then say select everything from account. Run that, And notice we get back user ID 1, so it was automatically created for us. We have Jose, password, jose@mail.com, and then we have the created on. And notice the last login is currently null. So we were able to successfully insert into this new table. Now let's go ahead and practice inserting into the job table. So recall the job table, if we take a look at it here, has the columns job ID and job name. Recall job ID was serial, so I don't need to worry about actually providing a job ID. So what I'll do here is I'll say insert into, and then we have the job table. The columns I'm going to insert is just the job name. So what I'll do here is say job underscore name. Then I'll say values that I'm going to insert here. And job ID is created automatically through serial, so I just need to say job name. Let's go ahead and have the job name be like an astronaut. So we'll say astronaut. Go ahead and run this. We get back query returned successfully. Let's check on that by saying select everything from job, run it, and now I can see I have a job ID 1, job name astronaut. And let's add one more job just so we can explore this job ID. So we'll say insert into job, and we're going to insert a job name. And we'll say values. Let's go ahead and have it be president. So we'll say president as another job, run that again. And if we check out the table again, select everything from job, notice that the job ID is automatically being increased for us, which is really nice. Okay, so we have this job table with some job options, and we have the account with basically kind of our fake entry into the account. Let's go ahead and finalize everything by actually doing one connection for an account job, essentially assigning the account I've made myself to a job. That's going to be a little different because we have that foreign key set for us. So what we're going to do here is we'll simply say, like we did, insert into. We will say account job, pass in a user ID, a job ID, and a hire date. I'm going to expand on this just so we can see the whole thing. Then we'll select the values we're going to insert, and we'll say user ID is 1 because that matches up with the first person we made in the account table. We'll go ahead and have him be an astronaut, so that's job ID number 1. And then the hire dates, let's just say current timestamp. So we run this. We get back query returned successfully. So let's go ahead and delete this. Say select everything from the table, which was account job. Run that, and I can see user ID 1, job ID 1, and a hire date. Let's go ahead and show you what happens if we try to insert someone whose user ID doesn't exist. So I'm actually going to do Control-Z a few times to get back this command. So just Control-Z a few times should bring you back to insert into account job. And I'm going to insert, let's say, user ID 10 with job ID 10 at my current timestamp. Currently, we don't have a user with user ID 10, and we don't have a job ID with job ID 10. So when I try to run this, notice what happens. We get this error. And the reason we're getting this error is because it's violating the foreign key constraint. So just like we have to provide information for things that are not null, we have to make sure that when we're inserting something that has a foreign key constraint, that it actually exists in the other tables. This is the exact kind of behavior and error you want. Otherwise, we're doing some sort of link that doesn't actually exist. There was no user ID of 10, there was no job ID of 10. So keep that in mind. These constraints will do things like stop information being inserted into it if it actually violates the constraint. Okay, so that's the details for how to insert data into a table. We'll see you at the next lecture. Welcome back, everyone, to this lecture on the update keyword. The update keyword allows for the changing of values of the columns in a table. The general syntax is as follows. We say update, then what table we want to update, And then we can say set column equal to, and then some apparent value that we've chosen for that column. And then we can also specify conditions for where the update should occur. So let's show you an example. We can use that account table we created earlier to say something like update the account table, and then set last login column equal to the current timestamp, where the last login is null, which basically says if there is a null value in the last login, go ahead and update all those values to be the current timestamp. You can also reset everything without any where condition. So if I wanted to just overwrite and update all the last login entries, I could just say update account, set last login equal to current timestamp. I could also set everything based off another column. So we also have the created on column. I could just say update account, set all the values in last login equal to created on. I could then also add in a where condition on top of this. We could also use another table's values. This is sometimes known as an update join, even though it doesn't use the join keyword. So the way this works in general syntax is we choose the table we're updating, such as table A, and we say update table A and set the original column, which is part of table A, equal to some new column part of table B. From table B, where table A.id is equal to table B.id, which is essentially where that joining is taking place. So we just figure out some key to match these two tables on, and then we say set the original column within table A equal to table B.new column. We can also return the rows that are affected. So if you just run one of these update commands, you don't see any results, but if you do want to see particular columns that were affected, you can set the command, something like update account table, set last login column equal to the created on column, and then you can say returning and choose the columns you want returned, and it's going to return the rows that were actually affected. And you can return all the columns or a subset of columns. It's really up to you. Let's go ahead and explore this further in PgAdmin. All right, to begin with this, I'm going to take a look at the account table we set up earlier by saying select everything from account. Notice I'm connected to that learning database. And so far, if you've been following along, you should just have one entry in this account table. If you have more than one, that's okay. So we have this username, password, email created on, and currently our last login is null. So let's go ahead and change that a couple of different ways using update. So one thing we can do is set it to some sort of value, just all over. So I can say update account, and then say set last login, and I could set it to the current timestamp. So I could say something like set it to current timestamp. I run that, and notice it doesn't actually give you an output, so we'll have to ask again to select everything from account to see the change. Run that, and if I scroll over, now I can see the last login matches the current timestamp for when I ran that. Let's go ahead and just have it match the created on column. So to do this, we're going to say update account and say set last login equal to created on. Run that. So it looked like that worked. Let's go ahead and check on that. Select everything from account. Go ahead and run this. And now if you ran that, you should see these two match exactly down to the sub-second because it's directly lifted off the created on. And finally, let's explore how we could do an update based off two tables. So to do this, we're going to explore that job table we created. So again, we have this job ID, job name, and then recall that not only do we have the job table, but we also had, if we expand on this, the account job table. So we're going to say account job, run that as well, and it looks like we have a hire date. Let's go ahead and change the hire dates based off another table. Now, the procedure here is really just for syntax purposes. The actual logic behind this won't make too much sense as far as why anyone would want to change the dates for this hire date based off another table. So just keep that in mind. This is really just for a syntax example. Okay, so how we're going to do this is I'm going to update from this account job table, and I'm going to set the hire date equal to, and let's use the account table, and let's use the created on date from that. So we'll say update account job, set hire date equal to account.createdOn from the account table. So we have to specify what's the other table. And then we're going to do the following. Essentially, this is where the join comes in. We're going to say where account job dot user ID is equal to account dot user ID. So we run this. It was successful, which means if I were to select from account job, notice here the actual timestamp. Let's just go ahead and take a look at the subseconds. So 1909. And now let's take a look at the account. And it should be the exact same 1909. So again, that's the syntax for updating based off the results from another table. Very, very useful to know that. In this particular example, maybe that logic of the reasoning behind it didn't make too much sense on why you would want to do that. However, that was really just for the syntax example. So again, you update table A, set what you actually want to update from table B, and then show where you're actually matching that up, which is why this is known as an update join, even though we're actually not using the join keyword. And then finally, I want to just show you the returning keyword. Let's go ahead and go back and update our account table. Let's just set the last login equal to, again, current timestamp, essentially just resetting it a little further into the future. So we'll update account, set last login equal to current timestamp, and then I can say returning, and I can return something, basically whatever columns I'm interested in, such as email and let's say last login. And let's also grab in the created on, just so I can compare them. We run this, and that successfully ran. And in addition to that, it returns back whatever columns you were interested in. That way you don't need to do that select second step just to clarify or double check that your results went through. Okay, that's it for the update command. I'll see you at the next lecture. Welcome back, everyone, to this quick lecture on the delete clause. As you may have expected, we can use the delete clause to remove rows from a table. For example, we could say something like delete from, then choose the table name, where, and then some sort of condition, such as column row ID equal to 1. And this would remove the rows that have a row ID of 1. We can delete rows based on their presence in other tables. For example, we could say delete from table A using table B, where table A.id is equal to table B.id. Essentially, where there happens to be a match in between these two tables, we'll go ahead and delete those rows from table A. You can almost think about this in the same way that we had an update join. This would be kind of like a delete join. And then we can delete all rows from a table by simply saying delete from table. Similar to the update command, you can also add in a returning call at the very end to return rows that were removed to see what was removed from the table. Let's go ahead and just quickly explore this with PgAdmin. Okay, here I am in PgAdmin. What I'm going to do is just explore the job table. So we'll say select from job, and right now we have two jobs, astronaut and president. Let's go ahead and add in a new job, and then we'll go ahead and remove it. So to add in a new job, we already know that we just say insert into the job table. We only need to specify the job name column since job ID is a serial key, and that will be automatically filled in for us. So we simply say job name, values, and we can choose some values here. So I can say something like, let's go ahead and say cowboy as our job. We run this, and that worked out for us. So if I say select from job, we see now cowboy is the third job. Let's go ahead and now delete that. So we'll say delete from, and then we say the table name. And if I just ran this, this would delete all the jobs. So I want to specify a condition, and there's lots of options here, but I could say something like where job name is equal to cowboy. And then I can also add in a returning call to actually see the columns that were removed. So we'll add that in as well. So what this is saying is delete from the job table where the job name column is equal to cowboy, and then return the rows that were deleted, job ID and job name. So I run this, and note it returns back the rows that were deleted. Keep in mind, if I were to try to run this a second time, I don't get anything back because it was already deleted the first time, which means there was nothing to delete the second time around. So if I now say select everything from the job table, I see only astronaut and president. Okay, so pretty straightforward. That's the syntax for the delete statement. Thanks, and we'll see you at the next lecture. Welcome back, everyone, to this lecture on the alter clause. The alter clause allows for changes to an existing table structure. It has lots of use cases, such as adding, dropping, or renaming columns, changing a column's data type, setting default values for a column, adding check constraints, and even renaming a table. Let's look at just a few examples for the general syntax for these cases. The general syntax is alter table, table name, and then some sort of action call. For example, if you wanted to add columns to a table, you would say alter table, table name, add column, the new column name, and then specify a data type. You can remove columns by saying alter table, table name, drop column, and then the column name you want to drop. You can alter the constraints of an existing column by again using alter table, table name, alter column, the column name, and then you can do things like set a default value, you can drop the default value, you can remove or add in a not null constraint, such as setting a not null constraint to add one in, you can drop a not null constraint, you can add just a general constraint by saying add constraint and then the definition of the constraint name, like a check constraint, etc. So let's go ahead and explore some examples since there's lots of things we can do with this alter table command. Okay, here I am in PgAdmin. Since we're going to be doing so much altering and editing to a table, let's go ahead and create a new table first. We'll say create table, and we'll have just this table be called general information. And let's go ahead and have just a couple of columns here. We'll say an info ID column, which is going to be serial and based as a primary key. Let's have something else called title. This will just be like the title of some information. Say 500 characters max. And let's say for now, it cannot be null. And we'll add in one more column. Let's go ahead and have this be some person the information is related to. Again, variable character, we'll say 50. And let's have it be not null as well as unique. All right, so very basic table here. We'll go ahead and run this. Okay, so the table's created. Let's select everything from that table just so we can see the columns. So select everything from the information table. We have info ID, title, and person. Let's do a couple of things first. Let's go ahead and rename this table. So the way we do this is by saying alter table. We choose the current name, which is information, and then we say rename to, and this will change the table name to something else. Let's go ahead and call this table new info. We run this and we successfully alter the table, which means if I were to try to select from the information table, I get information does not exist, which means I need to use the new name, which is new info. And again, we get back this empty table. So that's how I can rename the table. If I want to rename just a column, I can do this. I can say alter table, new info, rename column. Let's go ahead and rename the column. So the way this works is we say rename column person to, and then the new name. Let's go ahead and say people. Run that. And if we select everything from new info, I see now person is people. So obviously a lot of things you can do here with this alter table command. The next thing I want to do is show you how you can use the alter command in order to alter constraints that already exist on certain columns. But to do this, first I want to show you how we could try to insert data into this table. So I'm going to say insert into new info, and I want to insert, let's say, just a title. recall that people was also not null. So I'm actually not going to provide people on purpose here. We're going to say values, and let's just have title be some new title. And if I were to run this, I get back an error saying null value in column people violates not null constraint. Okay, so we have two options. Either I can add in people and then add a value for it, or I can try to remove this not null constraint using alter table. Obviously that affects it permanently for the table on a table level, but this is just to show you the alter command. So I'm going to say alter table, new info, alter column, people, and then we're going to drop the not null constraint. If I wanted to set a constraint, then I would use set, and that adds a constraint. If you want to remove a constraint, you use drop. And recall, this not null can be anything. It could be dropping the unique call, the not null call, any sort of constraint here. Okay, so let's go ahead and run this. Okay, so I successfully altered that table. Now what I'm going to do is if I take a look at my query history, I can actually grab that old query of insert info. So let's go ahead and copy this. You can also, I'm pretty zoomed in here, so might make it look a little strange, but in yours you should see insert into. Go ahead and copy this. You can even copy it directly into the query editor. So I'll just click that. So we're trying to now insert into new info, title, values, some new title. Let's go ahead and run this, see if it works this time. And notice that it was able to work because I had removed that not null constraint. So if I select everything from new info, run this, we're able to add in some new title and keep people as something null. If you ever get confused or stuck or have trouble remembering what the actual calls are for the alter table command, you can always go to the documentation and look up alter table, and it has a whole synopsis of the different variants you can use, such as rename to the table, etc. We can also show you different actions that are available, dropping columns, adding columns, altering columns, etc. So lots and lots of different options here and examples. And if you start scrolling down, it has even more detail on each of these commands, such as alter constraint. There's also things like dropping constraints, etc. So lots of different options here. It's all for you. It's all here for you in the documentation. Okay, thanks, and I'll see you at the next lecture. Welcome back, everyone, to this lecture on the drop keyword. Drop allows us to completely remove a column from a table. In PostgreSQL, this also automatically removes all of its indexes and constraints involving the column. So it'll remove things like check constraints, not null constraints, unique constraints, everything that's associated with that column. However, what it does not do is it does not remove columns used on other things that are dependent on it, such as views, triggers, or stored procedures. If you do want to remove a column that has those dependencies for views, triggers, and stored procedures, which we're going to talk about in more detail later on, you can add in an additional cascade clause in order to just remove that column and those associated dependencies. The general syntax for a drop call, for dropping a column, would be alter table, table name, drop column, and then the column name. To remove all those dependencies I previously mentioned, you can say alter table, table name, drop column, provide the column name, and add in the keyword cascade, essentially cascading that removal to all those dependencies. Now, if you try to drop a column that does not exist, you'll get an error in PostgreSQL. So it's really common to add in an if exists keyword clause before the column name in order to avoid the error. So that way it only drops the column if that column name exists in that table. If you want to drop multiple columns, it's almost like adding in multiple column values. You simply say drop column 1 name, comma, column 2 name, comma, etc. Okay, let's go ahead and see a quick example of this in PgAdmin. All right, here I am in PgAdmin. Recall that we have this new info table that we created when playing around with the alter commands. Let's go ahead and drop the people column. So we'll do the following. We're going to say alter table, new info, and we're going to say drop column, and then say people. We run that, it worked out correctly, which means if I now select everything from new info again, run it, I don't have that people column anymore. Let's see what happens if we look at our query history, try to run that drop again. So I'm going to copy this to my query editor. This is the same thing we did last time, alter table new info, drop column people. Go ahead and try running this again. You'll notice you get an error. It says column people of relation new info does not exist. But if I add in if exists right before people, what it's going to do is going to attempt to drop the column only if it exists. And instead of getting an error, you'll get back a notice saying column people of relation new info does not exist, skipping alter table. And then it'll say query returned successfully. So instead of an error, it just gives you this message. All right. And that's basically all there is to dropping columns. Pretty straightforward exercise. Thanks, and I'll see you at the next lecture. Welcome back, everyone, to this lecture on the check constraint. The check constraint allows us to create more customized constraints that adhere to a certain condition, such as making sure all inserted integer values fall below a certain threshold. So for example, let's imagine we're creating a table called example, and this is going to just have an example ID column, which is a serial primary key, and then we have an age column. And let's say for this particular example, we have to make sure that the people are over 21. So we'll say age, small integer for the data type, and then we add in this check constraint. And after the check constraint, we just have some condition, such as the age column must be greater than 21. And we can also set conditions based off other columns. So let's add in a new column called parent age, and then again, small integer as the data type. And for its check constraint, it's going to say that the parent age column must be greater than the age column. And so if you try to insert a person into this table who has an age that's less than 21, or if you try to insert a person here that has a parent age that is less than their own age, since that doesn't really make sense, we'll go ahead and produce an error. Let's explore this concept a little further in PgAdmin. To show you what we can do with the check constraint, I'm going to create a new table, and we're going to create a table of employees. Let's say employees have an ID, and well, let's say employee ID, that's going to be serial, and it's going to be a primary key. Then they have a first name, which we'll say is a variable character. Let's give them up to 50 characters for their first name, and no constraints here. Or we can add something like, let's say not null. They need to have a first name. And then something else we can do is give them a last name, variable character, let's say 50. Let's say they also need a last name. And let's start adding things maybe like a birthday. So if we say birthday column, this should be a date. And let's make sure that the birth date happens to be greater than or past 1900. So we'll say check that the birthday is greater than, and we'll say 1900 January 1st. Basically, we won't allow anyone to say their birthday is before the year 1900. And now let's add in maybe last two columns. One column to say the date they join. So we'll say hire date. This is a date. And we want to make sure to check that their join date or hire date happens to be greater than their actual birth date. And let's change this to birth date, just so it's clear that we're not referring to just the day of their birth, but the actual date of their birth. Okay, so we have this birth date, and their birth date has to be greater than January 1st, 1900. And then we have their hire date, and their hire date has to come after the day they were born, which makes sense. And then finally, let's go ahead and give them a salary. This will be, let's say, a numeric data type. Just go ahead and have it be integer or numeric. So we'll say data type is integer. And then finally, let's go ahead and make sure that the salary has to be greater than 0. So we can't accidentally input a negative salary there. So we have these various columns along with these check constraints. You have a check constraint against a date, a check constraint against another column, and a check constraint against some salary or integer. We run this, we've created that table, looks good. Let's go ahead and now attempt to insert someone into this table. So we'll say insert into the employees table, and then we're going to go ahead and grab those columns. So those columns, we don't need to worry about the employee ID, that was a serial column. We'll say we're going to insert a first name, a last name, their birth date, their hire date, and then their salary. So those are the columns we're going to be inserting into. And now let's choose some values, basically just made up values. We'll go ahead and I'll choose some of my values here. We'll say Jose, Portilla, and then what I'm going to do is let's go ahead and add in some birth date. I'm actually going to insert some wrong values so we can see the check constraints at work. So let's say I was born on 1899, let's say 11/03, and let's say I was hired in 2010/01/01, and let's give me a salary of $100. So if I try to run this, I'm going to zoom out just a little bit so we can see kind of everything at once. We'll go ahead and run this. I get back error, new row for relation employee violates a check constraint on the employee's birth date check. Okay, cool. So it looks like that worked. Let's go ahead and change this. I'll make this 1990. We'll run this, and now I was able to successfully insert that. Let's go ahead and add in a new employee. Let's call them Sammy. Let's call this Sammy Smith. We'll go ahead and have them be the same birth date, but now let's accidentally say we put a -100 as their salary. We'll run this, and it looks like that fails the constraint for employee salary check. So remove that negative, run it again, and it looks like everything's working. So if we select all from employees, run that, I have both Jose and Sammy, same birth date and same salary. Okay, something that's really cool to notice here is that the serial actually kept a count of those failed attempts to insert. So I failed on my first attempt to insert, which means it started the primary key at 2. Then I failed another attempt, and then when I got Sammy right on the 4th time, it gave it a primary key of 4. So this actually lets you know that rows were either removed or insert commands failed before Jose and after Jose. So kind of an interesting aspect of the serial data type there. Okay, thanks, and I'll see you at the next lecture.